Good morning, dear students. Welcome to another session of DSP architecture and algorithms. So, in the previous session, we started off with architectures of programmable digital signal processing devices, in which we discussed few of the architectural features. We discussed regarding the multiplier. Uh, then we discussed what are the bus widths which we have to utilize. Then we came across shifters, and in that we discussed regarding barrel shifters. And in previous class, we started off with the MAC unit. So we discussed regarding this multiply and accumulate unit. So based on the previous this thing itself, so few other concepts what we have to go around. So with respect to MAC unit, right, there are few things what we have to check out. That is overflow and underflow what might occur. Now this is because you can just observe that now if I just assume that accumulator is having some fixed size, accumulator is having some fixed size, and if the product exceeds this, the product that is multiplication and addition together exceed the storage limit, then there will be a overflow. So underflow might occur when the number is very small. That is what it results. So that is here we can see that we can encounter overflow and the underflow condition. This may be due to the word size which is present in the multiplier, and it is also due to the size of the add or subtract unit and the accumulator. So it is all relevant to this. So here it is n and n. So it is dependent on how many bits this is operating, on how many bits this is operating, and how many bits this can store. So based on this, overflow condition may occur. That is word size of the inputs with which the multiplier is operating. Now here if you are giving say 2n bits, but it is a n bit multiplier, then you are actually exceeding its limit, and due to which there will be a overflow. And then in order to avoid such kind of instances, right, we go for using different techniques in order to identify these things or avoid this overflow or underflow conditions. Now here frequently used methods to avoid these conditions are using a barrel shifter. That is, so here what I do is if I have two, just for example, if I have n plus 2 bits as input, so 2 bits are excessive. This is acting for n bits, 2 bits are excess. So what you do is you shift 2 bits towards right. You shift this entire information 2 bits towards right, and then you go ahead by giving the n bits, by giving the n bits to the multiplier. So by this, what you're doing is you are avoiding the overflow condition which is present over there. So one is using the barrel shifter at the input, and even at the output, right? If you have shifted it here, result, whatever result you are getting here is the shifted version. So again, to get back the original information, again you have to shift it in the opposite direction. And sometimes what happens is intermediate results also have to be checked out. But generally, what we do is we use barrel shifters at the input and at the output. So that we try to avoid this overflow or underflow condition. Now, apart from that, we have some specification termed as the guard bits, which are provided in the accumulator. Now, if you just look at the accumulator, what is accumulator taking in? It is taking in the addition, addition of these say 2n bit of numbers. So if n bits of numbers are multiplied, maximum size what we can obtain is 2n. So 2n bits, when 2n bits are added, what happens is we'll be getting a result. This result may exceed with some amount of numbers. Now that is dependent on how many numbers you are adding. So log n to the base 2, if you remember. N is the number of inputs what you are giving to the adder. That is, if n numbers are being added, So it is nothing but you are continuously taking multiplication and you're continuously adding. For example, here 256 are there. You're adding 256 numbers over here. So if you're adding 256 numbers, what happens? 8 bits will be produced in excess in the addition part, in this part. So 8-bit excess can be produced. It is not just you're adding this and this number. It is not this numbers. It is how many numbers. What you're doing is you're multiplying and accumulating it. It is like you add the first number, then go to the next one. So result of this two you take and add it to the third number. Then result of this one you take, add it to the fourth number. So you continue. So you're accumulating. It is the continuous addition of all the numbers what you're doing. So here what happens, if I took an example of 256 products. So here it can be exceeding by 8 bits. So what I do is, if I don't want to lose the accuracy and I want to avoid the overflow underflow condition, what I do is accumulator is provided with 8 bits of excess, 8 bits in excess. So these 8 bits what they have provided, that is based on the example what I'm specifying. These are called as the guard bits. These are termed as the guard bits. So we provide guard bits in the accumulator. Now there is another technique which is called as saturation logic. Again, we'll be checking these things in barrel shifter. We have checked it out. So these two again we'll be checking in the next slides. So saturation logic. So here what happens is whenever we are adding numbers or subtracting numbers, there is a tendency that the number might, the addition might result or multiplication might result in a number which is larger than the largest possible integer which this accumulator can store. Now, for example, if it is just 2 bits, so 1 is the largest number that it can store. Now, by a general this thing, if I add say binary 1 to this, what is this result? It is 100. Now, this since accumulator is just 2 bits, now what is happening is it has overflown, but at the same time, what is happening is it is exceeding the largest number what it can store. That is, it is getting saturated. It is getting saturated. Say I'm say going for unsigned numbers. If I go for signed, then again it changes. So if it is 0 is the lowest number what I can store. Now, for example, if you have 0 and you subtract -1 to this, so what happens is this turns out to be -1 in your decimal form. So what is happening? 0 is the number which this accumulator can store, lowest number which it can store. Now -1 is lower than 0. So again, it is saturating in the other direction. So such kind of conditions when they occur, so we have to check what is happening. And if such conditions happen, for example, if 1 is the maximum number, you add it, you are getting 1. You get a overflow condition. You try to identify whether that there is a overflow or not. If there is a overflow, then what you do is you store the accumulator with the largest possible value in this case. And if it is going below the lowest possible value, you store the lowest value in the accumulator. So by this, you are just trying to avoid the saturation. So accuracy is lost, but what you're trying to do is you're trying to provide the saturation logic to avoid the overflow and the underflow condition. So next, so use of shifters, that is these things. How to avoid the overflow and the underflow conditions? Shifters. So we had seen in barrel shifter that how shifting operation can be done in just one cycle, one machine cycle. So here, why that shifters are required, as I specified, if you're going for addition, uh, if I'm adding n number of bits. So here, somewhere we had specified. So here we can see these problems, right? This we had discussed, these all problems. So if 64 numbers are being added, 6 bits are in excess. If only 16 bits are there, then 6 bits additional have to be provided to the accumulator. If you remember all these stuff, so you're trying to avoid the overflow. So in order to do this, what we do, we provide 6 bits excess. If this is not possible, then what we do, we can go for shifting 6 bits towards the right before you go in addition. So at the input of the multiplier, before giving the data to the multiplier, what you do is you shift it towards right by the number of required bits, so that you are avoiding the overflow condition. These are just a few examples what we have discussed. And once we shift it, we get the sum, right? That sum is actually shifted version of the original information. So here you have shifted by 6 bits. So you should again shift it back by 6 bits towards left. Here we have shifted it towards right. Here we should be shifting it towards left. That how it is done. It is done by multiplying with 2 raised to 6. So the same thing we are looking forward here. So you provide a shifter at the input and the output of the multiplier. This is all to avoid the overflow and the underflow condition. Now at input, they normalize the data samples and the filter coefficients, because these are the two parameters which are provided as the input. So that is, if I just look at convolution, right, it is x of n convolved with h of n, where h of n is the filter coefficients and x of n is the data samples. So normalize in the sense you are shifting and doing that operation, and you are normalizing the entire stuff. That is the data and the filter coefficients. Now at output, what you are doing, since you are normalizing, so that is I shifted, for example, I shifted the data towards right in the previous example by 6 bits. So now I should shift it back by, shift it left by 6 bits. So here we are specifying this as normalization and this as denormalization. So we are denormalizing the overall result, and this result is stored in the memory. Now here, if you just look at the output shifters, for what purpose they are used. Now here we can go ahead with discarding the redundant sign bit which is present in the 2's complement. Because sign bit only one bit is required, your MS bit specifies that when we are adding or multiplying, right, what happens is even that sign bits gets altered. So and only one bit is sufficient for that purpose. So for that purpose, what happens is you might be generating instead of one bit, you might be generating 2 bits. So redundant sign bits might be possible. And if you're multiplying 3 numbers, so sign bit of all the 3 numbers have to be accounted. So when that is the case, say 3 bits might be in excess, only one sign bit is sufficient. So that is what redundant sign bits imply. So when you actually do the multiplication with the binary number, that time you'll be able to identify. So 1, 1, 1, 1. So you'll be getting 3, 3, it is 6. So this one is sufficient. But you should take care of all these things. So first you should take 2's complement and then go and add these then go and perform the rest of the operation. Here we have done it directly. So first take 2's complement and then do the operation. So once you get that result, what will happen is you'll be getting some numbers in excess. So if I can avoid that, so that can be done with the help of the shifters. Then shift the output by several bits as per the requirement. So that shifting operation, as we specified in this case right here, we shifted in the previous example by 6 bits. So how it was 6 bits? Because 64 numbers were being added. So in that case, so log n to the base 2, this turns out to be 6. So based on this one, you have to shift it. So this is done when there are several preceding zeros or ones. So what is this means? So if I have a number something like this, so here this much part is sufficient for me. This is actually like redundant part in this case. Similarly, if I have continuously this one, then we have to check out whether how much part is sufficient for me. So that for that purpose, we shift the data and then we perform the operation. But when we are shifting and performing the operation, at the end we should take care that we should be getting the same result. Okay, so those cases will be taken. Now here, why we go for barrel shifters that we had discussed, it will consume less machine cycle as compared to your other shifters which are used in your regular microcontrollers. So in one go itself, I'll be able to shift the entire data. That is, just activate the switch based on which how many shift you want. If you want three shifts, activate switch 3 S3. So when S3 is activated, what happens is this data is made available at B0, B1, and B0 and B3. and this will be happening at only one machine cycle. So whereas in the other case, if you have some information, so if you want to shift it three this thing, so first shift this, then this, first shift, then next shift, and after that the last shift. Now it depends on what logic. In this one, it is like you are following the MS bit. So for example, if this is the data, so whatever data is there, this will be retained, and next it will be shifted. So again, this will be retained and shifted. So here in this way, we require, say for example, 3 machine cycles, but that can be achieved in just 2 machine cycles in this case. So this is what is happening in case of barrel shifters. So coming down to the guard bits or the extension bits, sometimes also it is termed as extension bits. Now here why we require the guard bits. So as in previous this thing we have discussed, so let us look at the example. So here we have a Mac unit whose inputs are 16 bits, 16-bit numbers. So each input is of 16 bit. Now, if 256 products are to be summed, so there are how many this thing? There are 256 numbers which have to be added, So in the Mac unit, how many guard bits should be provided for the accumulator to prevent the overflow condition from the overflow condition being occurring? So here, if you just observe, we have 16-bit numbers which are given as input. That is 16-bit numbers which are given as input, and there are 256 numbers which have to be summed up, and it is specified that it is a Mac unit. So what is the first part of the Mac unit? Input is given to the multiplier, and the maximum result can be how much? 2 times n. So here 2 times 16, it is 32 bit. It is 32 bit, and the result can be how much? So if I give 32 bits here, so without guard bits, it is like 32 bits and 32 bits get added, and we'll be getting a 32-bit result. 32-bit result. So this is your accumulator. This is your accumulator. Now you want to avoid the overflow condition. So if I have to avoid the overflow condition, what happens? I should see how many numbers you are adding. So here, so when first number comes and second number are added, 2 numbers result I'll be getting. Then the third number will come, then it continues. So it will be continuing for 256 times. So here what happens is I'll be having log 256 to the base 2, that is um, 2 raised to 8. So it will be 8 bits in excess. So it will be 8 bits in excess, because 256 is 2 raised to 8, and 8 if I just take out. So I'll be having 8 bits in excess. So the I should provide guard bits or extension bits whose size is 8 bits. So this is done to avoid first the overflow condition and then to preserve the accuracy. These are the two things what we'll be doing here. So that is what is specified in this case. Okay. Now what about the saturation logic? Saturation logic. Now again, saturation logic has to be implemented to avoid the overflow and the underflow condition. Now when does overflow occur? If you just observe this thing, overflow occurs when the size of the result, which is resulting from the MAC operation, is larger than the largest value the accumulator can hold. So here if I just see, if accumulator is 32 bits and the result is exceeding by 8 bits. Now if it is able to store only 32 bits, the largest number, say if it is signed or unsigned, if you just think, if it is unsigned, it can store maximum of all ones. All 32 bits are ones. So that is the maximum result which it can store. Now if further some addition comes in, what happens is the result overflows. Now what about the underflow condition? Even that might occur. So the lowest possible number which this accumulator can store is 0, 0, 0. That is all zeros in unsigned condition. It is all zeros in an unsigned condition. So here what is happening? If I subtract some value from here, so 0 is there, this 0 comes over here, and I get a number, and you say performing subtraction operation. So when you perform subtraction, what happens is this number goes below 0 value. That is it is going in underflow condition. Now I should avoid these things. So now if the accumulator, what it is storing, that is the result of the MAC operation, is larger than the largest number or the value which the accumulator can hold, this gives rise to overflow condition. And the underflow condition occurs when the MAC operation results in a number which is smaller than the smallest value that the accumulator can hold. So this is what is happening in this case. Now, if you are taking signed and unsigned, right? Unsigned, assigned numbers if you are taking. So, for example, 00, 01, 10, and 11. So this is like 0. This is 1. This is actually this is like plus 0 and minus 0. I'm just taking an example. This is minus 1. So here, if I just observe, minus 1 is the lowest number what I can store, and plus 1 is the highest number what I can store. So that is what we are trying to specify. If it is larger than the largest value, that is say in terms of signed, it is plus. In terms of this thing, smaller than the smallest value, that is the smallest negative number what can be stored. So, but this can occur in both signed and unsigned operations also. Hmm. So I have to have some saturation logic. That is, you are exceeding the saturation. You are going beyond the largest possible positive integer and largest value, and the you are moving below the lowest possible value. So under these conditions, saturation occurs. So when this is the case, we have to try to avoid the errors. And now, if you remember in your programming aspect, right? If you have, say, this thing, you have something as 128 to 127 is the range of the numbers. Now, if you add 127 plus 1 to this one, that what actually this does is this goes around and wraps, and the result will be minus 128. If you remember this, so it will be wrapping around. If you're using signed numbers, right? This will be wrapping around. If you're using unsigned, also the same thing happens. Say the number is 0 to 255 maximum. So when you add 1 to this one, right, it is actually 256 in I aspect. But in your system, what happens is 256, it rounds around. It is like modulo addition, what you're doing here. So that is what is happening. It comes down and it takes as 0. So that is the avoid the error for this condition. That is wrap around error. So this arises because of these conditions. So we have to avoid these things. So now in order to do that, we have to put up some logic in the hardware in order to detect this uh, saturation and try to load the accumulator with the either the highest possible value or the lowest possible value. Now, so we'll keep track of these things. You will be providing a multiplexer for this one. So based on the sign bit of the MS bit, you try to choose either the lowest significant, lowest negative value or the most positive value. It is like you are choosing either the lowest value or the lowest value or the highest value. So either of these two based on the sign bit and based on overflow condition, overflow or underflow condition. So here CI is the carry into the MSB and Cout is the carry out of the MSB. Now here you can see that this is the XORing logic what they have used. So if I XOR these two and it results in either overflow or underflow conditions, then you load the accumulator based on that. So this circuit gets triggered whenever there is a saturation occurring, and based on that saturation, whether it is whether lowest number has to be stored or highest has to be stored will be decided by this CI, that is sign of the MS bit, input sign MS bit. So based on that, the accumulator will be stored. So for example, if I just took the example of minus 128 to 127. So if I say add 1 to this actually goes to minus 128. So this is like it is exceeding the highest possible value. So what I do is I store the accumulator with 127 itself. I'll store the accumulator with 127 because 128 plus 128 is not possible because 127 is the highest. So for all the operations, I'll be storing only this information. So this is with respect to the saturation logic. Now coming down to the next part, that is arithmetic and logic unit. So as the name suggests, you should be able to perform some arithmetic operations and logical operations. So what are the arithmetic operations? Arithmetic operations are the addition, subtraction, multiplication, increment, decrement. For multiplication, again, we have a kind of operation which for multiplication and addition together, we have MAC unit. And the logical operations are also required, that is ANDing, ORing. So in previous listing only we saw that here we require XOR, but this is the hardware aspect. But even in this one, right, we require a logical unit and or not. So apart from these, in your implementations also you have some other flags. So what is the purpose of the flag? Purpose of the flag is to indicate whether the event has occurred or not. Event in the sense, suppose you are adding two numbers. You are adding two numbers, and what has happened is here carry has been generated. Now, how do you keep track of whether carry is being generated? You make use of the carry flag. If, for example, if carry flag is set, it indicates that carry is generated. If carry flag is not set, that is, it is zero. It indicates that there is no carry generated by the result what you are performing. So just this is just an example. So these are the status flags what again ALU will consist of. Then apart from that, we should have the overflow management and register flag. So let us come to the status flag. So this is basically used to identify what is the status of the accumulator, which is actually required in a ALU operation. Now here again, it might be utilized to sequence and scaling purpose. Now, for example, you want to check out that, say, suppose you are just performing like jump zero. So if the result is zero, you jump to some label, jump no zero. So you are trying to control the sequence in which the program is being executed. Now here flags can be of different type. So we can have overflow flag, underflow flag, sign flag, zero flag. If you just continue, you can have carry flag. So there are n number of flags which can be present. So based on that, you can operate accordingly. Now these flags are set or reset based on some condition. Based on some condition, so a circuitry will be operated, and based on that, it moves up. So for example, here you have the overflow and underflow condition. So if overflow has occurred, based on that, it will go and set the overflow flag. If underflow has occurred, it will go and set the underflow flag. So this is with respect to the status flags. Now coming down to the overflow management, so we discussed what all things have to be present. Similar kind of approach will be utilized in ALU. So in Mac we have overflow and underflow management, right? The same way we'll be managing the ALU part. So these all together will help us to have some controlled aspect over the saturation logic. So even in ALU, the saturation might occur when you're using the accumulator. So how do I avoid that? Again, the same concepts what we have discussed over here, right? The same way we can go ahead. We can provide guard bits. We can shift the data at the input and shift the result at the output. So these are different approaches which are used in Mac. The same approaches can be utilized in your ALU. Can be utilized in your ALU. Now here, so what is the register file? Now this is basically used to improve the efficiency of the ALU. How it is used to improve the efficiency of the ALU? For example, you have some information in the memory, and you are executing some instructions, or you are doing some performing some operation. So you want certain part of This one you are executing. So whenever you are fetching this, this can come and sit in the cache. So if you remember your the same concept, so this is not exactly cache. I'm just comparing it with the cache. So this is kind of cache. So here what cache does is it stores the recently executed information and all. So if anything has to be accessed, right, it will not go to memory. If it gets to know that okay, it is in cache, so I'll directly access here. So what you're doing is you are improving the say access time. So in the similar way, if you have register files, right? So I'll take the data from the memory and store in the register file. So register files are directly accessible. So instead of going to the address of that location and then fetching it, what we do is we make use of register files. So this basically improves the efficiency. Now the file that is used to store the intermediate results. Suppose you're performing some operation and you want to store this information. So this information can be stored with the help of the register. So in registers, you keep on storing the intermediate results, and the final result can be stored in your say accumulator. So by doing so, what happens is basically you are improving the speed, improving the efficiency of the overall DSP system. So here, so again, if you just observe nothing, you are trying to avoid what in and out of data movement. So here, for example, if I come back to say Mac, if I just compare it with this case. So what you're doing is you're multiplying two numbers, intermediate result you're getting, you are adding those numbers and storing it. So again, you are going back, adding it with the next result, and this you're continuing. So intermediate results, what you're doing is you're storing it in this say register file, and final this thing you go and store it in the accumulator. So I'm just taking an example just to specify how it can be achieved. So this is what we can do here. So that is what they have represented. So here we have an accumulator. Instead of storing it in the accumulator, so I can fetch some information in the register file, and then I can go ahead, perform the operation, and store the final result in the accumulator. And accumulator also can be a part of that information. Okay. So this is instead of say I have stored a data over here which was in some memory location. So instead of going every time to this memory location, getting it, and then say performing the operation, what we have done is we have stored it in the register file, use this register file, and then perform the operation whatever is required. So you are avoiding the access to this location every time, and final result only you are trying to store in the in memory location somewhere. So in and out data movement is actually avoided in such cases. Now next, what should be the bus architectures and the memory? Now here we have three different specifications. Now when we have two kinds of approaches, one is von Neumann architecture and another one is Harvard architecture. Now here, if you just see in von Neumann architecture, based on this diagram, itself can make out. So here we have two different, we have one memory which will be accessed for both the purposes. That is for program purpose and the data purpose. So data will be stored in data memory and program instruction will be stored in the program memory. So that is what is happening. So in same memory, you are keeping both. But here, if you just observe in Harvard architecture, you have separate memory provided for the program memory and you have separate memory provided for the data memory. Now, what does this do is this helps us to access the information at a very faster time. That is, here what is happening, only one access is possible. But here I can access, for example, here I can access it at the same time at the same time. So program, I got the instruction that okay, I should add the numbers. So if I get to know that it is add, I get to know that the next two this thing will be numbers which will be present. So directly I can go and fetch the numbers from the location. So here what is happening? So once you fetch this address, then you try to get the access to the data. So first you're doing this, then this, but here I can perform it in some parallel kind of thing. So this definitely increases the execution speed. This increases the execution speed. So this is one way of providing. Now, for example, so here if I have something as add B. So A is accumulator, it is implicit. So accumulator will be containing the information already. So here I'll check out, okay, instruction is add. So then I get to know that accumulator has to contain one data, and next data is dependent on what is the register. So I'll go and fetch that information into B. So now I'll be adding it. So here what happens is you are adding it in this form. So two this thing fetches will be required. Whereas in this case, what happens is you go and fetch, you get to know, okay, you go and fetch the instruction. You go and fetch the
Mhm.
instruction. It is like add this thing B. You get to know that you have to add two numbers. So you go and fetch the information from the, you try to get the access to the address and try to fetch the accumulator content and the address content. So, but all this thing will take one execution for this one, just example, one execution for this one execution for this one. But this is not the case in this one. So you get to know that, okay, add is there. So when I get to immediately know, I can go and fetch the information for A during this machine cycle itself. That is the first one when add instruction is being fetched, and next one in another machine cycle. So here, for example, three machine cycles, but I'll be able to complete this one in two machine cycles. So now the next question might be, can I increase this memory? So that is what they have done here. Now, generally, if I am specifying, for example, add B, here two operands are there. Here two operands are there. So you have fetched the instruction, you got to know that you have to add the numbers. So what are the numbers? It is A and B. So in the next machine cycle itself, you go and fetch A and you go and fetch B directly. So in one machine cycle itself, you are able to fetch this information. You are able to fetch this information. So what is happening is you are definitely improving over the execution, but at the same time, what you're doing is you're increasing the cost. So all has to be taken care. So if I have to reduce the cost, then I have to say I try to avoid using excess memory. I try to go ahead with this kind of structure. So this is also possible, but it increases the cost. But it increases the speed at a very high rate because both the operands will be available in one go. So that is what is happening in such cases. Okay, there is another thing what we have to look out is memory. So what kind of memory? It can be of on-chip memory. So what we have shown over here, the 4.8C. So this is the architecture what they have just shown. So as I mentioned, that this actually has advantages that speed of execution is increased, but cost also increases. So that is a disadvantage. And also along with that, you can see hardware requirement also increases, then complexity also increases. So in that is in this structure. Okay. So it is good enough, but at the same time, you should have some complex implementations, and so that I can fetch all this information in one go. So all these things comes over here. One possible solution to overcome such kind of this thing is to go ahead with on-chip memory. So on-chip memory is like a cache which is available over there. On-chip memory access is very fast. So in order to go ahead with these things, we can go ahead with the on-chip memory access. They have so these memories have dedicated addresses and data buses. This actually what this does is it reduces the pinouts which have to be given for the DSP systems. So whenever we are having such kind of approaches, right, pinouts also become important. I cannot have very large number of pinouts for the DSP systems. I try to keep it as minimum as possible. So even that also I try to fit in. Otherwise, what happens is it might consume more space also. So these are the things what we have to look out when we are dealing with DSP systems. So what are the issues which are related with the design of the on-chip? It is the speed and the size. So speed, because DSP systems have to be operating at a very high speed. So going and accessing the memory and fetching the information. So this on-chip memory should support that. So that is again possible because of the new technologies which have come in. So that is in a single execution cycle what we are looking out for. So that is what they have specified here. So on-chip memory should support these kind of approaches which are used in systems. And size, I cannot keep on-chip memory too large or too small. So depending on the optimized parameter, we try to decide what should be the size of the on-chip memory. If it is too large, then again DSP system itself will consume more amount of space. So I have to look into all these things. If more size or more on-chip memory size is provided, again cost again increases. So it is all interlinked. So we should have a compromise between all these things. So here we have some this thing. What if the entire architecture of 4.8b and 4.8c is provided with on-chip memory? Now here what happens is instruction fetch, operand fetch, and the result storage execution will be done in one machine cycle. So here that is what they try to specify. You fetch the instruction, so you get to know that instruction it is add, immediately you go and fetch the data which is required. And once the data is available, you can go and get the result and store it in the memory. And the same thing can be done over here. So this can be done at a very faster rate. Okay. So speed of execution can be increased, but what happens to the memory? But memory will consume more space, which basically hinders the scope for the other functionalities which have to be put on the DSP. So for example, I want to put in even Mac unit along with that barrel shifter and all. So if I am consuming more amount of space for memory itself, then the other functionalities will be hindered. So that is what they want to specify here. So several other methods also we can use to overcome this issue. So here just a few things. So just read the highlighted terms. Provide only two blocks of on-chip memories to hold the operands required for the execution of the instruction. So one is this, on-chip memories can be designed such that they can be accessed more than once in an instruction cycle. Then along with this is the third option, on-chip memories can be configured for different uses at different times depending on the requirements. So these are the three different approaches.
ನನ್ನ ದೋಸ್ತನ ಪ್ರೈಮ್ ಐತಿ ಅವನ ಆರ್ಡರ್ ಮಾಡೋದು ಯಾರ್ ದಿವಸ ಬರ್ತದಂತ ನಾರ್ತಕ್ ಬರ್ತಂತ ಹೇಳಿ ನಾವು ಇಲ್ಲ.
Okay, so these are the different methods what I use to solve the issues over here. So provide two different blocks of on-chip memories, which helps to hold the two operands. For example, A and B, what we are discussing, it will hold the operands and it will increase the execution speed. Again, the problems what I discussed will be coming forth here. More space, more on-chip memory, more the cost, more the space it will be consuming. Now, can I design the on-chip memories such that I'll be able to access the on-chip memory twice in one instruction cycle? So by this, in one instruction cycle itself, I'll be able to achieve the other stuff. So can I again configure the on-chip memory to be operating in different ways at different times based on its requirement? So here, what happens is you can see the complexity of the implementation, what is involved in such cases. You can do it, but again, complexity increases. Okay. So this is all for today's class. So let us meet in the next session.